when it comes to simulating aerodynamic simulations, here are the list of steps that you need to do. Now, these steps are not simplified. Like when I used to work when I used to work with Red Bull on their internal flow and external flow problems, we would do virtual wind tunnel analysis all the time, and this is basically the list of steps that we carry out. So the first thing that you do is create something called as a virtual wind tunnel. So the next step is you take your CAD model. All right. Now for computational fluid dynamics, you only need the surfaces that are interacting with the fluid. For example, when you're doing aerodynamic analysis, your engine does not have to be present. You just have to include the outer body, which is in contact with the fluid. So wind tunnel is basically, to understand it very simply, is a box. But this box has been created using some kind of a CAD software. And whatever it is that you're testing, you basically put that inside this box. This is the object on which you're going to do the flow analysis, as simple as that. Then what you do is you provide something called as initial conditions and boundary conditions. Why do we do that? Does anyone know why we provide boundary conditions and initial conditions? I wouldn't say that that is entirely true. If you do a little bit of reading, computational fluid dynamics is about solving certain types of equations. Now these equations are called as partial differential equations. I'll be showing it to you later. What you're doing is when you're doing a virtual wind tunnel test, you're basically solving this equation inside your wind tunnel. And since these are equations, since these are partial differential equations, you need boundary conditions, right? Just like you need them when you're solving them in a piece of paper. Usually your conditions basically represent your flow conditions. Your boundary conditions would be something like, what is the flow rate? So for something like 60 km per hour or 80 km per hour. Now, how would you basically decide this particular speed? In the meantime, the next question that I wanted to ask is, what should be the inflow speed for our virtual wind tunnel test? Should it be 60 km per hour? Should it be 80 or should it be 20 km per hour? All right, so you see 60 to 80, right? So what's the accurate answer? Well, see, it depends ideally on what type of track you're running that you're going to race. Again, many students don't don't do this much type of analysis. So usually, like if you take a look at F1 cars, right, that is what you guys need to try and learn and maybe apply some of those concepts. So aerodynamic simulations are typically performed based upon your racing conditions. This does not take into account only the top speed, but it takes into account the type of track. So let me ask a simple question. Say that you have two types of track. So this is kind of your first track, right? And we have another track which looks like this. Again, I hope that you guys can see that I'm drawing the top view here. Let's call this as track A and track B. So now, what would be the speed at which you conduct your wind tunnel tests? Drag forces. So what you would do is you would have a baseline case where you basically say that, okay, at 16 km per hour, this is my wing parameters. This is the drag force that I get. Okay, so if I'm going to be running or basically racing in track A, then I need to get as low drag force as drag force as possible, and then I can modify my wing parameters, wing designs, and then try to see if I can get a lower number. Now, on the other hand, if you're going for track number B, the answer is obvious. You're looking for more downforce. So if you're looking for more downforce, well, you will obviously increase the angle of attack in your front and rear wings, so that it generates more downforce. And then you will also be looking at the distribution of downforce. So if I look at the car from the top view, do I have a symmetrical distribution or is there an asymmetry? Right? These things needs to be looked at, and you change the CFD analysis. You change the CFD calculations accordingly. The other thing that people would do is if there's a lot of turns, you need to basically look at the downforce at different yaw angles. So what's the yaw angle? Well, so for example, I'm going to try my best to actually draw a car here, right? So let us say you have a car like this, right? So let us say you have a car here. This is what you call as a zero yaw configuration. I hope many people know this. So yaw is basically saying the angle by which your car is rotated with respect to the z-axis. So a zero yaw means it's the flow is going straight on. A 10-degree yaw means the car would be slightly tilted the car would be tilted like this. Minus 10 would mean the car would be tilted the other way. So when you are having a lot of turns, right, you can basically estimate what is the most common yaw angle at which your vehicle is going to turn. And then it makes sense to do CFD analysis on that to make sure that your downforce distribution and your downforce number still makes sense. Okay, so this is two techniques that you can put in place right away. The first thing is, say you have a race, make sure that you get your track conditions. And for those track conditions, try to figure out if you're testing it for max speed or close to max speed, or you're testing it for downforce. Then you need to have a number for what is the average speed at which you make the turn, correct? That is a number that you most likely have. You take that number and that would be your inflow condition.